Hello and welcome to my YouTube channel DNA Structure. In this tutorial, this is the second part. I am going to calculate base shear by using response spectrum method, and also I will do the same thing in Etabs and we will compare the results. To proceed, we will need the stiffness matrix and mass matrix. For stiffness matrix, I am considering the coordinate from bottom to top. So the formula for stiffness matrix will be this. If we consider the coordinate from top to bottom, then the case will be different. So here I am considering the translational stiffness. So the formula will be 12EI by L cube, where E is the modulus of elasticity and defined by 5000 square root FCK. Square root FCK, where FCK is characteristic strength of concrete. And I is the moment of inertia, which is calculated by BD cube by 12. So the size of column is, that is cross section, 300 by 300, D cube by 12. So our stiffness will be 12EI by L cube. Here in each floor we have 4 number of columns, so multiply by 4 and this will be our stiffness. So this will be in Newton per mm and simply multiply it by 1000, so we'll get this in Newton per meter, and the value of stiffness will be same for each floor, so we'll get this value as stiffness matrix. And mass matrix we have calculated earlier as a seismic weight, and simply multiply that value to get in kg, multiply by 1000 to get kg, and the horizontal seismic coefficient is z by 2 I by r SA by g. Here the SA by g will be different than equivalent static method, and we have zone factor as 0.36, impotence factor 1.2, response reduction factor 5. Now to calculate the value of SA by g, we will calculate first time period, because SA by g depends on time period. So to calculate the time period, we will use MATLAB. Here I have written the code and I will explain it. Now simply run it and I will explain. We have mass matrix as this value, type in this form, and for stiffness type in this format, and this DISPM simply displays the mass matrix, and similarly DISP displays the stiffness matrix as displayed here, that is this value. The mass matrix is this, the stiffness matrix is this. The display command simply displays the values. So for this calculation we are using k minus omega square m, and its determinant is equal to 0. So here v and d is equal to eig km, so it simply gives the eigenvector and eigenvalue, where v is the eigenvector and d is the eigenvalue. So here W11 means it's simply take the value from first column and first row. Similarly, W22 means second column, second row, and so on. So it simply displays this value. So it here this value. So square root of this will give us natural frequency, which is this value. W equal to square root of d means we are getting the natural frequency because here W is square. So square root of d will give us the natural frequency. And for time period, the formula is 2 pi by omega. Here we are picking W11 means first column, first row, and W22 means second column, second row, and same goes for T3. So we are getting time period as this value, this time period. So we can simply normalize this value manually, but I have done this by using this code. So although the value of 1 is at bottom, but I have normalized this in such a way that this represents the coordinate of second floor, and this for first floor, and this for ground floor, and same goes for mode 2 and same for mode 3. Now we have time period as this. Simply copy and also copy the matrix, mass matrix. Simply copy that mass matrix, mode shape matrix. Simply copy and we'll use for further calculation. Now we'll calculate the W phi, where W is seismic weight and phi is mode shape matrix for each mode. We are calculating the same for each mode, and we will also calculate W into phi square for each mode. So we have the value for seismic weight as this, and we have the value of phi. So simply multiply I square and we will get this value, and simply add the value of W phi. We will get this as 190.92, and simply add the value of W phi square and we will get the value as 155.77. Do this for mode 2 and mode 3 as well. Now we will calculate modal mass, which is given in code. This is modal mass. It is summation of W phi square, and it is square of summation of W phi divided by G summation of W phi square. So here the seismic weight is kilonewton, so I am multiplying it by 1000 to get in Newton, and in formula it is divided by G. So finally we will get this value in kg. So simply divide W phi and summation of W phi and to the summation of W phi square. So this goes for mode 2 and mode 3 as well. Now we will calculate the percentage of total weight, which is simply calculated by dividing the modal mass to the seismic weight, and the same goes for mode 2 and mode 3. Here the contribution of mode 1 is 91.72%, and contribution of mode 2 is 7.27%, and for mode 3 it is 1.01. Similarly, this pk is They are also in code. pk is mode participation factor. Simply it is the summation of w5 and to the summation of w5 square, which we have calculated. So simply divide this w5 divided by w5 square. Similarly do for mode 2 and mode 3. Now we have time period. Now we will calculate the value of SA by G, which depends on time period. Now go to code. Now this time we will use response spectrum method, this table, and our time period is 0.24. For mode 1 it is 0.24. So it lies in, for medium stiff soil it lies in 0.1 to 0.55. So the value of SA by G will be 2.5. And for mode 2 the time period is 0.089, and 0.089 lies in this region. So the value of SA by G will be 1 plus 15t. So it is 1 plus 15 into time period. It comes as 2.33. And for mode 3 the time period is less than 0.1, so it will be 1 plus 15t again. So it comes as 1.94. Now we have the formula, which is Z by 2, I by R and SA by G, and so simply multiply all the values, so we'll get horizontal seismic coefficient for each mode. Now we'll calculate the value of Q and V, which is given in code as this Q, peak lateral force is Q, which is defined as A phi PW. We have calculated all these parameters, so simply we will multiply, and V is story shear. So let's calculate. Here we have seismic weight, mode shape matrix, so simply use that formula to calculate the Q for each floor. We are calculating the Q for each floor, and simply we sum the value to get the value of B for each floor. Now same goes for mode 2 and mode 3. Now we have calculated the value of Q and V for each mode. So we'll combine this by using SRSS, which is square root of sum of square. So here V3 is square root of this V from mode 1, V from mode 2 and V from mode 3. If we combine by SRSS, then we'll get V3 as 10.33. For this is for second floor, and V2 is for first floor, and V1 is for ground floor. We'll calculate by using this value by using SRSS. Now we'll calculate the value of Q, which is externally applied load, which is Q3 is equal to V3. Q3 acts on second floor, and Q2 acts on first floor, and Q1 acts on ground floor. So it is simply calculated as this. So Q2 is equal to V2 minus V3. This V2 minus V3, and Q1 is V1 minus V2. So if we add all these values, then we'll get the base shear as 25.34. Now Let's do the same thing in Etabs. Now I will continue the model which we have created previously. So I want to show you one thing, that we are considering as MD of shear building model. So the one of the assumption is flexural rigidity of beam is too high than flexural rigidity of column. Now we will define this in Etabs. Now I will simply modify this. Here I am not touching the value of E. Instead, I will modify the value of moment of inertia in both the axes. Simply insert very high value of moment of inertia and we are done. Now I will define the diaphragms as actually it is defined by default, so we will assign the diaphragm in each floor. Similarly, we will assign for story 2 and for story 3. Now we will define response spectrum function. So go to response spectrum function and select IS 1893 2016 and add new function. Simply rename it. Our impedance factor is 1.2 and soil type 2, response reduction 5, and simply click OK. Now I will define load case, the response spectrum case. Here U1 indicates x direction and our function is res, which we have defined just now. So we'll combine by SRSS, and I will add one more for y direction, although it is not important. And select U2 for y direction and our response spectrum function and combine the results by SRSS, and we are done. I think we have defined all the things correctly. So I will run this in 2D. Let's run this in 2D. So it will be simple to understand. Now go to tables by Control plus T, and in analysis result go to structure output and select base reaction. Here the base reaction we got is 24.05, and in our calculation we got 25.34, so it is quite close to our manual calculation. And now let's check the time period of each mode. So go to table by Control plus T, and in modal information select modal periods and frequencies. So the time period here for mode 1 it is 0.352, and in our case for mode 1 I think for mode 1 it is 0.35, and here we are getting 0.24, and for mode 2 it is 0.08, here it is 0.11, and for mode 3 it is 0.06, and here we are getting 0.06. So there is quite difference in mode 1. Let's see. In mode 1 is 0.352, and now let's check we have defined the things correctly or not. Now let's run once again. Again we are getting as 0.352, which is not closer to our manual calculation. Let's run this in 3D. We are getting different time period than our manual calculation. This because the value of moment of inertia is cancelled by the software, so apply this to high for both the axes. And now we are done. Let's run this in 2D. Now the value will be quite close to our manual calculation. Now for mode 1, the time period given by Etabs is 0.267, which in our case it is 0.247, which is quite close. And for mode 2 it is 0.089, and from Etabs it is 0.095, which is also quite close. And for mode 3 in Etabs it is 0.065, and in our case it is 0.063. So we got quite closer results to our manual calculation by Etabs. So I think this concludes our tutorial. So thank you for watching this video.